Okay, so I'll continue from the discussions in the last class. So this is our 7th lecture, and this is today is 3rd of September. So we moved on from the differential part of the vector calculus, and we started looking at vector integral calculus in the last lecture. In particular, what we talked about in the last class was we first introduced the idea of integrals, but we immediately moved on to the concept of integrals. And line integral is along a path. And if you have a vector field f, so it could be a path. Let me call that path to be some gamma. So that's one kind of line integral. And the other kind of line integral is the integral along a circuit. These are the two types that we talked about. And what we mentioned was that most generally the line integral would not be path independent. Okay. But there does exist special kind of vector fields, and in particular these vector fields have the property that they can be written as the gradient of a scalar function or scalar potential. For such kind of vector fields that obey this property, the line integral is path independent. When I say path independent, if it is not a closed circuit or not a circuit line integral, then it just depends on the endpoints. And these we already know are what we call conservative fields, or these are conservative fields. And what we showed was that if you do the line integral for such kind of vector fields, you can write them as limit say to be the gradient of the scalar function. And this was one of the important results that we arrived at in the context of line integrals. What I also showed to you how to parameterize it, how to go ahead and do these line integrals. I also talked about the notion of work done and how when you're trying to calculate work done, it automatically you end up calculating this or working through these line integrals. So all these I have discussed in the last class, and towards the end of the last lecture, I moved into the next type of integral, which is the surface integral. And when I talked about surface integral, we have talked about all these things earlier, but still it makes sense to start from the surface integral for today's class, because that would be the main point of discussion for today's lecture. So just like in the case of line integral, the physical property that one is usually interested in where such an integral comes, it is work done. Similarly, in the case of surface integral, typically these vector surface integrals, you think of them when you are interested in calculating the flux of a vector field through some surface. And I talked about these closed surfaces. So let's say you have some arbitrary closed surface. Well, let's call it S. And this closed surface, what I mean by closed surface is that it encloses a volume within it. And let's say you have some vector field through this surface. And you can think in terms of heat flow when one is thinking about these kind of problems. And one can assume that this vector field that we have written, it represents the heat flow through a unit area in unit time. So what it represents in this physical system is heat flow per unit area per unit time. And what one wants to calculate is the total heat flow. So through the surface. So what one ends up doing, and this is the standard way in which one can think about it, that you first consider a small surface element and you ask the question, what is the total heat flow through this small surface element? So when I'm saying surface element, you automatically know that we are talking about this small area. And that makes sense because we have already defined this heat flow as per unit area. So you are going to multiply it by some area in order to know how much heat flows through that area. We also know that the component that we are interested in, so let's say that the normal to this small element is some, the direction is given by some n hat. So it would be along, so heat flow through this small area, let's say this is something small area dA. So heat flow through this element will be equal to the area times the component of this vector field perpendicular to the area element, implying it is along the direction of the normal to the area element. The way you want to think about this area, and I'm going to use it in today's class also. So when one is thinking about a surface that encloses a volume, so remember that when we discussed the concept of the direction of a plane, right? So area, we said there are two possibilities up. So if it's a plane like this, so it's up and down. There are both these possibilities, and there we very carefully defined which is the correct direction. Right? You use the right hand, and we defined it in that way. When you have a surface that encloses a volume, the direction of the area element is always the outward normal. So that is the convention, and that will set everything in place. So you're always looking at the direction which is the outward normal. So the direction in which heat is flowing is along this n hat, and in the manner in which we have been treating everything, we can write as the multiplication of the area element with the component of the vector field H along the direction normal to the area element. So I hope this is clear to everybody. So most generally, you simply write. Now, our objective is really to calculate the heat flow through the entire surface. But we know that once we are able to do it for one of these, we can do the same computation for many of these small little area elements in which the entire surface is being divided. So to calculate the total heat flow, we will sum over the contributions from all elements. So imagine that what you are doing is you are dividing your entire surface into many of these little area elements, and we are doing the calculation for each one of them, and then we are adding the contribution from all elements of the surface. Since these area elements, we have assumed that they are extremely small, they are infinitesimal. So we can replace this summation by an integral. And write it in the following. And so let me put a S over here to indicate that this is a surface integral. So you understand that this is a two-dimensional integral now compared to the previous one, the line integral, which was in single dimension. So you can write it as a double integral, dA, where if dA is one dimension is x and the other is y, so it's some change in x and some change in y, you can write as dx dy. Okay, so this is the physical idea behind the surface integrals. Obviously, it's completely general as far as calculating the integral itself is concerned, but you may want to think in terms of heat flowing, and the specific example of taking the vector field that is there to be a heat flow or a fluid flow, it maps to the idea of the flow. But remember, this is extremely general. It has not it is not necessary that something is flowing through that surface. It could just be a simple vector field itself. It doesn't need to be a completely physical quantity which is flowing out of the surface. So just remember this, because when we talk about electric fields, it's not really flowing like a fluid is flowing, or how heat flows through something. That is not the case over here. From here, there is an interesting observation that you can make. So let's say I take my surface, and remember it encloses a volume. So let's say that we separate the volume into two parts. So we divide it into two parts. So imagine that this is the entire volume, and we partition it at some point. So we are cutting it at some point. So now we have the entire volume being divided into two. And the surface that encloses this volume, let's say this curved part for the first volume component. So I hope that the picture is clear to everybody. So one part of the volume that I am thinking of is this, and just separating it out a little bit. The second part of the volume that we are thinking of is something like this. Okay, so you are just imagine that you have partitioned it, and the surface that encloses let's call it SA, surface or the part A, so surface, the curved surface of the part A. Then this one, let's call it, this is common between part A and part B. So we have divided it into two parts. We are calling them part A and part B. So the curved part, I write it as the surface as SA, the other one as SAB. This is also the common thing. So this is SAB. Okay, so that's the physical or the picture over here. So there are now two surfaces after we have partitioned it. The surface one, which encloses a part of the volume, and that has this part which we call S sub A, and then the surface which we call AB. And the second one, there is another closed surface which encloses the volume, that is made up of the surface which we call B and the surface AB. And let's say that there is some vector field. So let me just draw a vector field over here. So let's say there is some vector field which I will call as C. I'm just drawing one arrow, but there's a vector field over there. This is just not to clutter the figure too much. So now if we ask the question that what is the flux of the vector field C through the surface S1. So we just figured out a way to calculate it. What we want to do is we want to calculate the surface integral over this closed surface S1. We have broken it into two parts, and we can write this integral as a sum over both the parts. dA where I'll come to the normal component in a moment. You can do the same thing for the surface S2, or for the closed surface S2. So flux of vector field C through the surface S2. So this would be equal to, in the same manner, so this is what we would be doing if we were asked to calculate, if the problem was such that we partition the entire volume into two, and we ask the question, given our understanding of these surface integrals, what is the amount of what is the flux of the vector field, given a vector field, of course. So we are just going to conduct the surface integral. However, do notice the last integral for both of them. So I want to draw your attention to these two integrals that we have over here. And these, realize that the surface that we have, this is this shared surface between the two partitions. We have defined the normal to a surface as outward to the surface itself. So it's always pointing outward. So if you are looking at this particular surface, so the outward normal would be, the arrow would be pointing towards the other one. If you are calculating over for the second, or if you are calculating the second integral, then the arrow, the normal, is pointing in the reverse direction. So I hope this is clear. The outward normal, so let me call it N1, and for the other one it would be N2, but it will be in the opposite direction. All other things remains the same. The surface is the same, everything is the same. It's just the direction of the outward normal that is going to be opposite. And if that is the only difference that is there, then one integral is the negative of the other one. And if that is so, and now I ask the question, so maybe let me use another page, that what is the flux of the vector field C through the surface, entire surface S. We know that this flux through S will be equal to So let's call it flux through surface S would be equal to flux through the surface S1 plus the flux through the surface S2. But what we have just shown a moment ago, that when you add these two, what is going to happen is that the second integral, which is along that common surface, since one is the negative of the other, they are going to cancel each other, and hence what we will be left with is this would be equal to flux through the surface SA plus flux through the surface SB. And these are the outward surfaces. So even though we have partitioned the volume and we are asking the question that what is the total flux, what we realized via this is that the total flux is just the sum total of the flux through these outward surfaces. The contribution due to the inner part, which is the common part, it just cancels out each other. And what this gives to us, or what it rather tells us, that for any way, in any way that you can divide the original volume, it is most generally true that the flux through the outer surface which encloses the volume, so you can partition the volume in whichever way you like. And you can, if you ask the question, what is the flux? It only depends on the sum of the fluxes over all the small components, the outer components, because the inner ones, they are going to cancel each other out. So you may want to think in the following way, that let's go back to our enclosed surface figure again and assume that, so it's enclosing a volume. This is a two-dimensional thing, so that shape itself is not, will not come. But imagine that you partition it into many small volumes. Okay. And if you calculate the flux through each of them and add them, then you will get the flux through the surface. And this very simple observation that we have just made, it leads us to the next thing, which is a complete general interpretation of some of the things that we have talked about. So I hope that what I have just said is clear to us. The concept of the surface integral, we introduced it by thinking about the flow of heat, for instance. Having done that, having identified it, having defined the relevant components of it, we have made this rather interesting observation, which is a fact also, that we can partition, we can divide the original volume in any way that we want into many small volumes. And then if we calculate the flux through all the interior pieces that we have just divided the volume into and add them up, that would give us the flux through the surface. So I hope that this idea is clear to us. And then let's go in and talk about, so let's take one of these boxes that I have been drawing and talk about flux from a cube. And this cube is quite small. So we are taking just one of them. So let's assume that we have a cube. So this is my X direction, Y direction, and Z direction. So one end of the cube is over here. Let me say that these coordinates are X, Y, Z, and this is an infinitesimal cube. So just some delta X from there, even though I'll draw it to be quite big. So this is x plus delta x, y, z. Another corner would be x, y, z plus delta z. This is x, y plus delta y, z. Let me now draw the entire cube. Okay. And we again ask that question, that what is the given a vector field. So let's say that there is some vector field, again let's call it to be some vector field C. So let's say given this vector field, I want to calculate the flux of the vector field through the cube. And in order to do that, what we need to do from the discussion that from whatever I have presented just now is I would like to take each of these surfaces and calculate the flux through each one of them. So I hope that part is clear to everybody. So we will have to do this calculation 6 times because there are 6 faces to the cube. And for each face, we are going to calculate the flux. So let's start from this surface, which we label as 1. This is the back face of it. And okay, so that is located at the value x. So that plane x remains constant, and the quantities that are changing is delta y and delta z. So that is the plane that you are looking at. And we calculate, so flux of C, of the vector field, through the face marked as 1. So what we will do, we will again do the same thing, which is we want to calculate this integral for that particular surface. We'll take an example also that will make things much more clear. But this would be the standard thing that we would try to do. Now we know what this dA, this element, is going to be for that particular phase. So dA, and this, at least the first one, I will write in detail, and the other phases we can just take it directly. We don't need to write it again and again. So for here, so this would be delta x, delta y, once you integrate it out. But right now you can write it as dx, dy. Let's say that the vector field is along this direction, some direction. It's not normal, it's along some direction to that face. And we'll take this direction mostly for what we are doing. Outward normal would be along the negative x direction for this particular face. And that is the only thing that I wanted to point out. Once you have identified it, then it's a straightforward integral to calculate. We can just go in and we can calculate the integral. And let's say that on this particular, the surface that we are, the plane that we are looking at, so we are looking at the x component. So I will write it as, when you take the dot product, what it will give you, the x component. I'll put a 1 for the plane labeled 1. There will be a negative sign because both of them are in the opposite direction, the unit vector and the vector field. Okay, so the unit vector is in the negative direction. And then once you have done this, we are taking it to be very, very small. So this plane is extremely small. So what we can assume is that over this plane, the vector field doesn't change its value much. So we are going to assume that there is no y and z dependence on this plane. Not generally true, but on this plane, because the size of the plane we have assumed to be extremely small. And then what we will have is the flux through the face marked 1 would be given by the component of the vector field along the direction which is normal to the surface multiplied by the area of the surface. The negative, I'll repeat again, the negative comes because of the way the directions are. You have the dot product. The constant value or a constant value has been assumed because we are just thinking of an extremely small cube. It's not the complete volume or the complete surface. So if you want to think about a large volume, we have essentially partitioned it into many small pieces, many microscopic pieces, and we are only worried about the flux through that particular piece. Okay, and even though I'm taking it to be a cube, or the treatment is completely general. We don't need to take a cube in order to show these things. The cube has been taken just because the calculations are simpler. Now, let me mark the front face as 2. Okay, let me put a 2 here. Okay, so this is this surface that I am now thinking of. If you want to calculate the flux of the vector field through the face mark 2, you'll do the same thing. Everything else remains the same. The only thing that changes compared to the previous one is that the direction of the area element is along positive x direction. Again, we will have this assumption that the value of the vector field over this entire surface, over this entire plane that we are looking at, the one which I have marked with these green lines, it remains the same. With that assumption and taking into account the direction of the area element, this flux is going to be the x component of the vector field on the face marked as 2 times the area element. I hope that till this part things are clear to you, because this is the essence of this is the basic building block of what I'm trying to put in front of you. So we started with, let me just retrace my steps one more time. What I did was I started with the idea of the surface integral. From there, I moved on to an observation about the surfaces or the flux through these surfaces, which encloses a volume. And the specific way in which I tried to put it in front of you was, if you were to partition your volume, and you may just think of 2 partitions, or partitioning it into a single partition that brings in 2 partitions. What you immediately observe is that if you were to sum the net flux from these independent partitions, if you wish, then it gives you the flux to the surface. From there, we stated that if you have a volume, you can partition it the way you like into as many of these blocks or whichever volumes you want. And then if you calculate the flux through each of these small ones and add over that, you'll get the flux to the surface. From there, we said, okay, all that is fine. So let us pick one of this and let's assume that it is a cube. So let us take one of these partitions and let's assume that it is a cube. and ask the question, what is the flux through this cube? In order to calculate the flux through the cube, knowing that there are 6 faces to it, we have to calculate the flux through all the 6 faces and add all the contributions. That's all that we have to do. We systematically take each one of them and we are trying to compute. There is an assumption that we are making, which is a reasonable assumption to make, is that since these are very small sized volumes, and the objects or the fields that we have or we usually have over such small scales, they would not show a huge variation. That huge variation can come if there is a discontinuity, but we assume that there is no discontinuity. These are all well-behaved fields that we are thinking of. So we assume it to be a constant over that particular phase, and we rigorously conduct these integrals. That is all that we have been doing. Right now, what we have done is we have taken 2 opposite faces on which the x value remains the same, and we have computed. So on the second surface, we have the x component of the vector field, the value on the second surface, whatever that is, multiplied by the area. At this point, we need to know, so we may want to know, how are these, so how is this cx2 related to cx1? And since we are just looking at very small distances, we can look at it as a perturbation from the value on that first surface, and we can approximate the value. What I'm trying to say is that you can simply do a Taylor series expansion at this point of time, and you can calculate the value at the other surface. This is under the assumption that everybody knows what a Taylor series expansion is. You've done a course in calculus, you might have seen it at other places. So I'm not really going to write the Taylor series expansion, but I'll just state it over here. So the value at the phase 2 would be equal to value at the phase 1. Then what you do, you take the derivative. So in going from phase 1 to phase 2, you are changing x, so the variation along that. And if you are to do this thing completely, you will get the higher order terms, the second order derivatives and the higher order derivatives. But since we are assuming that this is very small, so we can stop at the, we can approximate it via the first order term itself. And we can make the observation, or we can write it as approximately equal to, I'm going to drop the higher order terms now. So the flux out of the phase 2 and 1 from whatever we have just calculated. So if we ask the question, what is the net flux through the phase marked as 1 and the phase marked as 2, we are going to just add them up. So that would be, that is equal to and we have just obtained the relationship for the term in the parentheses, in the brackets. So we are going to approximate or use that expression that we have just obtained. And this would be equal to, it is exactly equal in the limit that it is going to 0, delta x goes to 0. Okay. And that is the assumption under which we are working right now. We can continue with this, but we don't need to now, because I can just now argue from here itself, and you can yourself try to calculate. So we can, for instance, take the surface on the right and the surface on the left. So let's call the surface on the left as surface 3 and the surface on the right as the surface or the phase 4. Okay, these are the ones on which the y value remains a constant. And we can ask the question, what is the net flux through these two, the phase labeled as 3 and 4? We will have this, we'll do the exact same thing, and we can immediately see that it will be the y component. On this phase, it's the normal is the negative y. So this is the direction of normal. And on this phase, the normal to the phase is along positive y. And everything is the same, just that we are now asking the question, what is the value of the field on phase label 3 and on phase label 4? So I'll let you convince yourself about it, but what you can show is that flux out of 3 and 4, you can write it as now. Similarly, I hope that this is clear. It's just that I don't want to bore you by writing all the same steps again, but it's the exact same thing with the exact same assumptions that we made in the previous case when we calculated the flux out of the phase 2 and 1. It's the exact same thing. Nothing has changed. And finally, the only two phases that remains are the top and the bottom phases. So let's label the bottom one as phase 5 and the top one as phase 6. And ask the question or calculate the flux out of 5 and 6. And this, now remember that one is at z, the plane where z is equal to z, and the other is at z plus delta z. And you are going to relate one, the value of the field at the plane where z takes the value z, and the value at the other one, which is the plane phase 6, which is where it takes the value z plus delta z. So this would be equal to the derivative of the z component with respect to z, delta x, delta y, delta z. And now if you ask, and this is almost where I wanted to take everything, that what is the flux through the cube, the cube that we are considering. So through the flux through this cube, the surface of the cube, we calculated via the standard definition, but what we have is the sum total of 3 terms. Realize that you have a product of delta x, delta y, and delta z. Delta z is the height, and delta x times delta y gives you the, so delta x, delta y are the length of the cube, and delta z is the height of the cube. And this is in fact the volume, and we'll write it as some delta v of the cube. So this product over here, for each of these pair of faces that we have, it will be delta v. The net flux is the sum total of all this. So it is the partial derivative with respect to x with respect to z times delta v. We also know in the notation that we have been using what this term is, the term that I have just highlighted. this is the divergence of the vector field C. That's by definition. So nothing to say over there. And what we have just shown is for this very, very small cube that we have considered. So for this infinitesimal cube, the divergence of the vector field, something that we have in fact already worked with, can be written as, remember this is extremely small, so I will say limit the volume going to 0. I'll divide by this volume that we have, the surface integral of the flux. And this in fact gives you the correct interpretation of what a divergence is. So when you say that the volume goes to 0, so you're going to shrink the volume to be very small such that it goes to a point. Divergence is the limit of this surface integral, which gives you the flux. So this is the surface integral over the vector field, in the limit that the volume shrinks to this point. The volume shrinks to the point, but the ratio, which is the ratio that we have on the right hand side over here, which is the surface integral divided by the volume, that is finite. So you are calculating the flux at a point most simply. So let's get rid of all the other jargons that I have used. So what you do is you calculate the flux at a point, and the flux at a point gives you the divergence. From the observation that we had made about, we can partition it into many of the small infinitesimal volume elements and then calculate for each one of them. So if I now want to go, or rather ask the question about the flux through the entire surface that encloses the volume, what I will do is exactly the way I have been talking about it. You know, for one, you are going to add for all of them. So what we will have is, we'll take many of these cubes and we are going to add over them. When we add over all the cubes such that it has covered the entire volume now, it's easy to see that the final outcome and I'm going to write surface over here, no longer cube, because it is the complete surface now. So let me, what was the notation that I was using? So I think I remember, delta V. And you are going to do it for the entire volume, because now we have covered this entire volume. Since we are taking it to be very small, let me write it as dV instead of delta V. And this gives you a very, very important theorem. So remember that first theorem that I had talked about was in terms of these of the gradients. That was the first thing that we had talked about. This is what you call the Gauss theorem. Which essentially what it says is that if you are interested, so it connects this flux through the surface with the volume, and the way that it connects is that if you are interested in calculating the flux through the entire volume, so for each point in the volume, if you calculate the divergence, okay, that is the right hand side of what I have written. So the right hand side is, remember the interpretation of this part, the divergence of the vector field. You are calculating the flux by shrinking the volume to a point. So just this part is, you, for each point within the volume, you calculate the divergence. You look at all the points. So you cover that volume with many, many points. You look at all the points and ask what is the total flux, the sum total of these, that is the integral, that is the right hand side. That is going to be the same as, so for each point in the volume, that is the exact same as if you just looked at the flux coming out of the surface that encloses the volume. I hope this is clear to everybody. Again, my assumption is that unless you ask, I'm only going to say the things that I think is making it clear. Okay, so if it is not clear, you need to ask. But this is the idea behind flux. So multiple concepts I have tried to introduce within this. I've talked about the concept of flux. I have talked about how these calculations, how the different quantities that we have been looking at. The divergence is the second one. We had talked about gradient in the previous one. So what divergence is and what exactly it is trying to calculate. So I hope that these things are clear to everybody. For completeness, let me go back to my example of heat flow. Because this was my starting point. Then I sort of digressed and I went into deriving all these things. So if you imagine that you have some volume which contains a certain amount of heat, and that heat per unit area per unit time, we said that we represented by this vector h. So if you want to calculate the flux of this of the heat through this surface, so the way we started was that we need to calculate this integral over the surface. So even though I write it as single integrals, I keep on repeating this. If it's a volume, it's triple integral. If it's a surface, it's double integral. So that is inherent in it. Okay. And now what we have just shown is that for a very small volume, if you are calculating the heat flow through the surface that encloses this volume, that you can write as the divergence of this vector that's the heat flow vector. Let's say that by Q I represent the heat per unit volume, that is inside the surface, that is enclosed within the surface. So because heat is flowing out, I know that this heat that is contained within the surface, or because there is a flux, the heat that is contained within the surface, that is going to change in time. Right? The assumption is that you are not putting any sources of heat inside it. You're not adding heat to it in any way. So if it is flowing out, it is going to go down. If it is flowing in, it is going, the net amount of heat that is contained within the volume, that is going to increase. So since this is per unit volume, since things are moving out or in, so there's a flow. I'm not really thinking about in which direction it is going to be. So I can ask the question, rate of loss of heat inside the, we have talked about cube, so let me just call it to be cube. In time, per unit time, and this is a continuous process, that's what I'm assuming. In that volume, delta V, the total amount of heat is Q times delta V. This is going to change in time. So for that, I take the derivative with respect to time. Because the way it is, the change is opposite and this will become clear immediately, but right now you may just think about heat is flowing out. So if heat is flowing out, the amount that is contained inside that enclosed surface, that is going to decrease, or the amount that is of heat in the volume, that is going to go down. So I put a negative sign for that. And this should be equal to what we have just arrived at. This is this part that we have been talking about. So what I can do is, again, I can write it to be, so I had the flux, which is the surface integral. If you want, you can put a cube, because we have taken the cube. So through the cube, let's say it. We said this is equal to the divergence, and this should be equal to dq dt q delta v. I can just compare these two and write the divergence of this vector field, which is heat, is the negative derivative with respect to time of the heat per unit volume within the surface, or that is contained. And what this tells you immediately, this is an, I might, okay, I'll point out to the importance of this equation. This is a conservation equation for the kind problems where you have such kind of flows of fields and vector fields. It could be heat, or just like we have conservation equation in mechanics. So it's the same kind of thing. But what I would like to point out is realize that if the rate of change of heat that is within that is inside that cube, if that is positive, the divergence is going to be negative. If, let's put a then over here. If the time rate of change is negative, then the divergence of this field is going to be positive. And what does this tell you? See, if the time rate of change of heat is positive, what does this mean? This means that more heat is being accumulated within that volume. That's why it is increasing over time, right? Whatever. So I hope these are clear. Again, these are side effects of not getting to see anybody. But if you have a first order differential equation such that the derivative is greater than 0, so it's a slope, right? The slope is positive. If the slope is positive, this means that as you move forward, the value is going to increase, right? It's the same thing over here. So let me remove this. Let's not get confused by another notation. But if the time rate of change is positive, this means that the heat inside is growing over time. Growing over time means that more is being added. So there is inflow. And that inflow property essentially is, and something that you have, we argued about it when we introduced the idea of divergence. But if the divergence is less than 0, this implies inflow. If this part is clear, then the second part should be absolutely clear to everybody, because it's just the opposite scenario. Now it's negative, which means things are moving out. Moving out, that outflow character, that is the divergence of the vector field. Being positive. So again, because I have said a lot of things and I don't want you to absolutely or get confused in the kind of things that I have been saying. The important relationship, if you are just thinking about working out problems, what kind of things you want to solve, is this one, the one that I have boxed over here, which is the Gauss's theorem. This is the most important relationship. But the physical idea, that is what my intention was, that the physical idea should be clear to all of us. And the physical idea it arises from the concept of flow itself. We put the word heat to the flow because we started thinking about the flow of heat, but it is completely general. And the important outcome of the entire discussion is the Gauss theorem, which essentially says that you can look at the divergence at each point within the volume, and then sum, which is the integral over volume. Or you can look at the surface, just the surface that encloses the volume. So this is a closed surface that we are always thinking of. And ask the question, if you were to make it into very small area elements, or points also, up to you, and then add the outflow or the flow through each one of those points, that is the surface integral now, either is the same. When we take up examples, it will become clear as to when one is more handy than the other one. But this is one important outcome. Since I'm on this topic, let me just point out another thing, and this I'll call it to be an aside. Okay, so don't take it to be a part of the course. I do, but this is something that I just wanted to show to you. Maybe it will appeal to a few of you. So what we just showed is the divergence of this field, that is negative of the amount of heat inside, the rate of change of the amount of heat per unit volume. Now, if you are thinking of a heat problem, you know that heat flow takes place because the temperature is not uniform. So heat flow itself is related to the gradient of the temperature. You are looking at the change, and the change gives you the direction. It's opposite to the maximum, and there is some proportionality constant, which I'll call to be K. So I can write this vector H that I have been talking about as the gradient of a physical quantity, of a physical field, which is the temperature field itself. I can plug this expression into what we have just derived. And what we will have is, these are operations that we have done. You will also see that not only in electromagnetic theory, this appears in a lot of places. When I introduced it, the second order derivatives, I tried to create a big deal about it. But the reason is that it sort of appears at a lot of places. So what you will have is you plug in the same expression, the negative cancels with negative. I don't want to write the entire thing. So you will have the constant K, the Laplacian of the temperature, that is equal to the right hand side. One more assumption, and now I am going to appeal to some of your earlier knowledge, or I hope that you have read. If you have not, then again take my word for it. So we are going to assume, the assumption is that the temperature of the material in consideration here is proportional to the heat constant, proportional to the heat constant per unit volume. Okay, so what I mean by that, delta Q I can write as the specific heat times the change in temperature. Or since again incremental change, so delta Q, you can say that is very small, you can write it as this dq term. So the right hand side now, this is what I just wanted to put in front of you. I can write as CV or the Laplacian of the temperature is equal to Cp divided by this constant. This is an expression. If you just observe it, you will see that the left-hand side is a second-order derivative with respect to the space coordinate. That is what the Laplacian does. And the right-hand side is a first-order derivative with respect to time. It is a very general expression in itself, even though we have derived it specifically in the context of this heat flow. This is what is called the diffusion equation. And that was one of the reasons why, or the heat equation, if you, in this specific instance, it is called the heat equation. But most generally, so I will say you have some scalar field, let's call it psi, that is equal to a constant, psi. It's something which is first order in time and second order in space. This d here is the heat constant, that diffusion constant, which is the ratio of specific heat to that constant k that we have taken. And what it tells you, because once you have these equations, you know exactly, either by solving it or by simulating it, whichever way, if there are no analytical solutions possible. But this is linear, so mostly under general assumptions, you should be able to, one is able to solve it. You're not expected to solve it. But what it gives you is, there is some scalar field, there is some physical quantity, and in time, so if you take a snapshot in time, you will observe something in space. You will observe a profile in space. If you want to know how that profile changes in time, it is the right-hand side that will give it to you. That is the rate of change with respect to time. And it applies to a wide variety of problems, not necessarily related to just physical concepts. It's much more than that. That is, of course, when you reach at that stage, hopefully you'll see some of them. But this is just for completeness. This is just to show to you that whatever we have been discussing, so we sort of stopped at the idea of divergence Gauss theorem. But if you just take a few more steps from there, there is a powerful outcome that is there in terms of the diffusion or heat equation. If some of you do a course in partial differential equations, you will see something like this. I'm not going to say anything more than this on this aside part. It has nothing to do with the main material of the course. It was just to show you something else, nothing more than that. Again, for our consumption, till here is what you should be comfortable with. I'm out of time. I wanted to do an, I'll start with that example in the next class so that you know how to calculate the flux based on the discussions that we had till now. I hope these are clear to you. Typically, what one ends up doing is just gives you the Gauss theorem and the general idea behind it. I've tried to do a bit more than that. I have tried to give you a more general idea and also how you arrive at the Gauss theorem itself. Okay. So I think I'll stop at this point, and if you have any questions, I can take those.